My name is Mason DeChico. I'm a PhD student at WPI, and this talk is about nearest neighbor complexity and Boolean circuits, which is a paper that I worked on with Daniel Reichman, who's a professor at WPI, and Vladimir Podolsky, who's a professor at Tufts. So the first half of the talk is going to be about nearest neighbor complexity. The second half will be about Boolean circuits, and I'll discuss some open questions at the end. So suppose we're given a set of red-blue colored points in R2. And based on these, we want to color a new point that we haven't seen yet. So one way to go about this is to use the nearest neighbor rule, which is just copy the color of the closest point. So on the left here, we would get blue. So this is a very simple and well-known algorithm, and actually was written down as early as the 10th century. It's often regarded as Occam's razor, and in the 1950s, computer scientists got a hold of this rule and started asking some interesting questions. So one of these questions is, how good is nearest neighbors as a classification rule? So in the 60s, Cover and Hart showed that nearest neighbors actually is quite good. It has asymptotically optimal error. So the more data it sees, the closer it gets to approximating the true function. Another interesting question is about efficient implementations of nearest neighbors. So we have the data structure problem here, which, given a set of Boolean anchors, how best can we load them into a data structure which enjoys both a fast query time and reasonable space usage? So we have two kind of very obvious extremes here, which is the brute force solution, where we just don't store anything and iterate over the entire data set every time. And we also have the opposite extreme, where we just store every possible query in a lookup table and get constant query time, but need exponential space. And it's actually conjectured that nearest neighbors suffers from what's called the curse of dimensionality, where any sublinear query time would imply exponential space usage. And one way that people have tried to circumvent this is to kind of relax the problem a bit and only require retrieving a approximate nearest neighbor up to some 1 plus epsilon factor in the distance. And actually, some very efficient data structures were developed solving this problem. But the focus of this paper is the more recent question of representational complexity of nearest neighbors, which is essentially questions of the form, how many anchors do we need to represent a given function? So this was asked for the first time in 2022 by Hajnal, Liu, and Turan, specifically in the context of Boolean function complexity. So we're trying to represent Boolean functions by anchors, which are either Boolean themselves or real. And this also has revealed some interesting connections to tropical mathematics, which we'll discuss in the second half of the video. So nearest, for the sake of this talk, is taken with respect to Euclidean distance. So in particular, we'll let delta be equal to the squared Euclidean distance between two vectors. And we'll note that when x and y are both Boolean, then delta is also equal to the Hamming distance between these two vectors, so the number of coordinates where they differ. And so with this, we can define nearest neighbor representations. So an NN representation of a Boolean function consists of two sets, positive and negative anchors in Rn, such that our function is equal to 1 if there is a positive anchor which is closer to x than any negative anchor, and f of x is equal to 0 if there's a negative anchor which is closer to x than any positive anchor. So note here that the inequalities are strict. We don't allow ties. And then we'll abuse notation slightly and let NN refer to the class of all polynomial size NN representations, meaning a polynomial number of anchors. And then H and N will be the same class, but the anchors are Boolean. So P and N are subsets of 0, 1 to the n. instead of Rn. And so nearest neighbor complexity asks questions like, which functions have small nn representations? Does nn have a significant advantage over hn? What do we lose when anchors are Boolean? And how does nn relate to other complexity classes such as circuits and decision trees? So let's do a brief example for each of these questions. For the first question, which functions have small nn representations? One thing to note is that every Boolean function does have an nn representation by taking every possible input point as an anchor. And for the example, let's consider the class of threshold functions. So these are Boolean functions which are equal to 1 if and only if some affine inequality of the input point holds. And an easy observation is that this class is precisely equal to nn representations with 2 anchors. And that's because both essentially realize containment in a half space. So to address the second question, does nn have a significant advantage over hnn? We will exhibit the parity function. So this is a Boolean function equal to 1 if and only if the number of 1s in the input is odd. It turns out that this function actually has an n+1 anchor nn representation. And that follows from the construction which just takes alternating positive and negative anchors along the diagonal of the hypercube. And it's pretty easy to see that this just slices the cube into the sections corresponding to each Hamming weight. And so this realizes the function. And on the other hand, when we require Boolean anchors, it turns out that the best we can do is the trivial representation. So every single possible input point must be an anchor. And for the third question, we will take the majority function. So this is a Boolean function which is equal to 1 if and only if the number of 1s in the input is greater than or equal to the number of 0s. And it turns out that there's actually a very simple HNN representation of majority when n is odd by just taking positive and negative anchors on opposite ends of the hypercube. And actually in our paper, we show that this 2 anchor representation doesn't hold when n is even. We require n over 2 plus 2 anchors, but I won't dwell on the proof here. So that kind of illustrates the general spirit of nearest neighbor complexity. And now we'll switch to talking more about circuits with respect to nearest neighbors. So in particular, what circuit classes contain NN? Can we implement NN on a depth 2 threshold circuit? And what circuit classes are contained in NN? So in particular, can NN help us prove circuit lower bounds? So for the first question, I'll briefly mention 2 constructions of circuits computing nearest neighbors. One of these is the canonical depth 3 circuit of Owen Murphy from the 90s, which computes arbitrary nearest neighbor representations. And so this is in the class of circuits which have an OR gate at the output, AND gates below that, and threshold gates below that. And actually, it turns out that when anchors are Boolean, we can construct a depth 2 threshold circuit with exponential weights computing any HNN representation. So now I'll actually start to get into the details of the main insight of the paper, which is this connection to min plus polynomial threshold functions or tropical polynomial threshold functions. So MPPTFs are expressions of the form a minimum of a bunch of linear forms on the left-hand side is less than or equal to the minimum of a bunch of linear forms on the right-hand side. And so these linear forms have integer coefficients, and we'll say the number of terms is equal to the total number of linear forms, and the maximum weight is equal to the largest integer weight or integer coefficient of any form. So we'll define the classes MPPTF infinity of the class of these expressions with a polynomial number of terms and unbounded maximum weight. And MPPTF poly n is the same class where the weight is bounded above by a polynomial. So one observation here that's bringing us back to nearest neighbors is that the distance from a Boolean point to an anchor in Rn is actually a linear form. So if we go ahead and expand out our squared Euclidean distance, since Boolean values squared are just the original Boolean value, then we actually do get that this delta is a linear form. And it was observed in the original paper of Hajnal, Yu, and Turan that actually NN and HNN are included in these classes directly. And that's just because the nearest anchor to X being positive is expressible as the minimum of the distances in P being less than or equal to the minimum of distances in Q. And since these distances are linear forms, we have an MPPTF realizing arbitrary NN representations. And what about the converse? Is MPPTF poly n contained in HNN, for example? Well, actually, it turns out that the parity function is contained in MPPTF poly n. And this follows just from a direct construction. And you can pause the video to digest this if you want. And so a simple corollary of this is that HNN is a strict subset of MPPTF poly n, and it's separated by the parity function because before we proved that the parity function requires 2 to the n anchors, so it does not have a polynomial size HNN representation. But such a result for real anchors and unbounded weights, we haven't been able to prove, but we do suspect that it holds. But okay, so suppose we wanted to prove that the conjecture didn't hold, that MPPTF infinity was contained in NN. Then what we would want is to be able to transform any given MPPTF into a corresponding NN representation of the same function. So that would mean given an MPPTF, or given a set of linear forms, we would want to construct anchors whose distances from a query point are precisely equal to the value of the linear forms at that query point. And then if we partition the left-hand side anchors into P and the right-hand side anchors into N, then we're done. And to approach this, we have the following idea. So consider the distance from the all zero vector to the query point. So this is just going to be the sum of each of the components of our input vector. And then consider what happens when we identify two variables, say x1 is equal to x2. Then the distance from this new query point to 0 is going to be 2x1 plus x3 ... So we've effectively introduced a coefficient on the first term by doing this. And in a similar sort of way, so consider what happens if we concatenate a 1 onto the end of our input vector. Now the distance from our new point to 0 is going to be equal to the previous distance plus 1. And so we've now added a constant term to the linear form equal to the distance here. So what we're kind of beating around the bush of here is the concept of a subfunction. So a subfunction of some function g is obtained by fixing input variables in the ways that we just did. So we can identify two input variables, or we can assign input variables to constants. So for example, subfunctions of this sum of input variables introduce coefficients and add constant terms, as we just showed. So suppose we let x1 is equal to x2 and assigned the rest of the variables equal to 1. So this would transform the previous linear form into 2x1 plus n minus 2. So with this, we define a closure operation. So given a collection of functions c, the closure c bar is the collection of subfunctions of elements of C contained or obtained by identifying or assigning polynomially many variables. So this just means the input dimension of the subfunction and the function it's a subfunction of are polynomially related. And this is actually a very natural operation. Circuit classes are already closed under this operation because circuits are closed under rewiring. We allow the input gates to be connected up to the first level gates arbitrarily. And so with this, we actually can show the closure of NN under taking subfunctions is precisely equal to NPPTF infinity, and the closure of HNN is equal to NPPTF poly n. And the proof is just an application of the first two ideas. We just take our linear forms and identify and assign input variables to realize the coefficients and constants. And from this, we obtain some corollaries. So, for example, we obtain that HNN is not implementable by a depth 2 threshold circuit with polynomially bounded coefficients. And that comes straight through NPPTF because there exists a function, which is the odd max bit composed with the two array and, if you're curious, where F has a pretty compact NPPTF representation, but it's known not to be in match-match. And similarly, we can have that there is a function in this class and of ORs of two array ands, which is not contained in NN. And that's because there exists a function f where f is not contained in NPPTF infinity, but it is contained in this class of depth 3 circuits. And so, in summary, we've shown equivalence between the closure of our two nearest neighbor classes and NPPTFs. And then we instantly get all of the known results about NPPTF, implying stuff about nearest neighbors as well. It turns out that these methods extend to the much more powerful class of k nearest neighbors. So this corresponds to the classification rule where we take the majority vote of the k closest points to the input. So it turns out that this class of k and n representations has the exact same closure relationship with a more general version of NPPTF, where instead of taking the smallest linear form on each side, we compare the kth smallest value on each side. And so from this, we obtain that when k is a constant, actually it turns out that k and n is exactly as expressive as nn under the closure. And when k is unbounded, we have actually k and n contains any function which can be written as an arbitrary symmetric function of majorities or an exact linear decision list, which are both large classes of Boolean functions. So now we'll just talk about some of the major open questions to come out of this work. The first one being, is NN closed under taking subfunctions? We already showed HNN is not closed because of the parity function. And we haven't been able to find a candidate function in NPPTF infinity that we think might not be in NN, which would show that this closure equality does not hold. Another question, which I didn't talk about at all in this work, is how does the bits of precision limit what NN is able to express? So one of the main open questions to come from another group from Caltech is, can we represent arbitrary threshold functions using only logarithmic precision? And finally, something that no work we're aware of has studied yet is, what is the expressive power of the approximate nearest neighbor rule, where we allow a 1 plus epsilon multiplicative relaxation in the distance. And yeah, thank you very much for watching. And here are the references.